Now let's use the method of least squares to see if we can find the line that best fits the points on our scatter plot. So how well the line fits the data will be discussed in the next section. For now, we're just going to focus on finding a linear fit to the data. So in general, if we have a scatter plot and if the dots roughly lie along a line sloping upwards, then there's a positive relationship between the two variables where higher values of the horizontal variable are going to be associated with higher values of the vertical variable and vice versa. And of course, a steeper slope to the line indicates a stronger relationship between the two variables. On the other hand, if the points roughly lie on a line sloping downwards, there's going to be a negative relationship between the two variables, and higher values of the vertical variable will be related to lower values of the horizontal variable. If the points lie roughly along a straight line, then no matter what the values of the horizontal variable are, the vertical variable remains roughly the same. So that line will have slope 0, and if the points form a disc-like shape or a non-linear shape, one can fit a line to the data, but visually you can see it's not appropriate to do so. So in the next section, you'll explore measures of the goodness of fit of a model for the data. Now let's look at our data for 2013-2014 season and for the fantasy points for the players. And we see that the data lies roughly on a line sloping upwards, but there are several lines that seem to be a reasonable fit to the data. So we can see that the line has a rough upward slope, and the relationship is going to be positive between the points scored in 2013 and those in 2014, and we have to pick from the lines with positive slopes which roughly fit the data. So in the method outlined below, we're going to find the line which minimizes the sum of the squared vertical distances between the points and the line that we're talking about. So here we have a picture showing the points in the data, and there's a line connecting them to a line that might be considered to fit the data. And you see the sum of the squared lengths of these lines is the thing we're going to try to minimize. And you can see that for the data, for the picture in the middle, that horizontal line has a much greater sum of square distances than the one on the right. So given a set of data points in the plane, let's call them x1, y1 down as far as xn, yn, such as those shown above, we can find an equation for the line which best fits the data in the sense that the square distances between the points and the line are minimized. So that's called the method of least squares, and this line minimizes the squares of the difference between the y values in the line and the y values for the points in the data. So that would be the squares of the lengths of the lines shown above joining the data to the line. So we're going to look for the line which among all possible lines minimizes the sum of those squares. When we find the equation of the least squares line, it gives us a linear formula which estimates the relationship between the variable x and the variable y, and then we can use that formula for predictions in the future. So recall that the equation of a line, it looks like y equals beta naught plus beta 1x, where beta naught and beta 1 are constants and y and x are variables. And the idea that we've been talking about is to find values of beta naught and beta 1, these are the unknowns here, so that the sum of the square distances between the points on the line and the y values in the data is at a minimum. So here y of xi is the value corresponding to xi from the formula y equals beta naught plus beta 1x, where we choose beta naught and beta 1 as we wish, and yi is the value corresponding to xi in the data point. So that formula given above gives us a mathematical expression for the sum of the square distances between the data points and the corresponding points on the line. And we have SSE stands for the sum of the squared errors. So to calculate the sum of the squared errors, if I pick a particular line, if I take my data points from 2013, 2014, the xi is the variable, these are the values for 2013, and yi are the fantasy points for 2014 for each player. And suppose I take a line that I think fits the data, a particular line, y of xi equals 150 plus 0.5 xi. So I've chosen a value for beta naught and beta 1, and then I can calculate the errors between the data points and the points on the line by just calculating yi minus y of xi. So y of xi is what I get when I plug xi into the equation for the line. And we could sum those, but we see there's a lot of cancellation. So you see in SE, the sum of the errors there, that there's a lot of cancellation there. So we square them, and you can see the sum of the squared errors at the bottom right there. So from the table above, you see for this particular line, the sum of the errors was minus 225. This is not a good statistic in measuring how well the line fits the data, because a lot of things cancel out. So you don't get the big picture. And so we avoid this problem by squaring the error. And we use the sum of the squared errors to measure how well the line fits the data. So naturally, a smaller sum of squared errors will indicate that the line is a better fit by this measure. So there is a unique line for which the sum of the squared errors is at a minimum, and this line is called the least squares line. So the methodology used to obtain the equation of this line is called the method of least squares for obvious reasons. And we can solve for the coefficients beta naught and beta 1 of such a line for a particular set of data by using calculus to find the minimum of this multivariable function, where the variables here are beta naught and beta 1, and the yi's and the xi's are the data points here, they're known. So we solve for the minimum of that function of two variables, beta naught and beta 1. So that's beyond the scope of the course, but I can give you some formulas later. By definition, let's just recap. The least squares line, y equals beta naught plus beta 1x for a set of data, is the unique line with the following properties. The sum of the errors is 0, so all of the errors cancel out when you sum them. And the sum of the squared errors is at a minimum. So that's smaller than the sum of the squared errors for any other straight line model you might come up with for your data. I can give you formulas for beta naught and beta 1, but in the next section you're going to see how to use Wolfram alpha to find these coefficients. There's a lot of calculation in finding the actual values of beta 1 and beta naught for large sets of data. You can see they're very similar to things we had for standard deviation, and in fact the reason for that is because we're actually using deviations as a measure for goodness of fit here. So for the above data, we can apply the formulas, and you'll find that the least squares line is given by beta naught is 177.06 plus 0.33x. And the sum of the squared errors for the line is 36,487.3, but this is less than the sum of the squared errors for any line that you might come up with when you plot it against the data. So we have a picture here of the line itself, the least squared line along with the data, and we can go on and use this line to estimate the fantasy points that a quarterback will score in 2015 given the number of points that they scored in 2014. So for example, if a quarterback scored 250 points in fantasy football in 2014, if history roughly repeats itself, then we might expect that roughly the number of points that he's going to score in 2015 will be approximately 177.06 plus 0.33 times 250, which is approximately 259.56 points. Now, there's quite a bit of calculation involved in finding the least squares line, and for a large number of data points, one can and probably should use statistical software. Wolfram Alpha, if you look up, you can also calculate the least squared line for a limited amount of data, and also if you have a TI-83 or above calculator, you can certainly calculate the least squared line. So we've included directions for the TI-83. You can Google directions for the TI-84, and you can also check out Wolfram Alpha, and I believe you'll be shown how to find the least squared line with Wolfram Alpha in the next module. So the process discussed above is called linear regression, and it's likely, of course, that there are a number of other variables which will have a positive or negative influence on the number of points scored, and I've listed a bunch of them here. So height of a player, age of a player, games played, experience, completion percentage, all of these may have an influence on the number of points a quarterback scores in the season. And so you can collect data on these variables and consider their relative weight or influence on the points scored in the 2014 season using a generalization of the method of linear regression we described above using multiple variables. So the method is relatively easy to apply, gives you kind of a linear formula for what to expect given values for these variables, and if you have some statistical software, it's bound to have regression on there. In chapter 3 of his book, Mathletics, Winston describes how to run such a regression in Excel and gives a nice compact explanation of how to interpret the results.